Thank you very much. So starting on a little bit of a sad note, I'd like to dedicate this talk to Toby, my teammate's cat who died suddenly earlier today. Let's just have 5 to 10 seconds of reflection to commemorate Toby. All right, wipe away your tears. No more sadness, let's get started. If you could encode the entirety of the internet into atoms, then you could fit it in a Yakult and still have space for the actual Yakult liquid. And then if you drank it, you might end up looking something like this. After reading a post on Physics Stack Exchange, I realized that if you were somehow able to do this, then the Yakult would collapse into a tiny black hole. So while you might not get to become this guy, you can still appreciate the vastness of data that's out there on the internet. And there will be more AI-generated images, so you have been warned, and some of them are definitely in the uncanny valley. While most of the internet is admittedly just cat pictures, there's also a bunch of data that describes how our systems are behaving or misbehaving. If you've got data, you send it to the cloud will sort it and change it up a bit, and it becomes queryable. It starts to look more like information. It's tempting to just send all the data that you can and think about it later. Especially if you're running a smaller system, you're more likely able to get away with haphazardly throwing your data into the cloud because there's not that much of it. So kind of like unloading a dishwasher, but just throwing everything in the closest cupboard. It works only if you live alone. When Oprah Winfrey did her famous car giveaway, she gave a car to the whole audience, almost 300 cars, at around 40 million Australian dollars. For obvious reasons, that quickly becomes unscalable with a larger audience. It's the same with sending data to the cloud. On top of that, there was also a hidden $10,000 gift tax that the audience had to pay. It's also a trade-off, like in computer land. And of course, everyone wanted cars after that. Audiences would come to the show expecting to get cars or other extravagant gifts. We want more data. We get used to the convenience of having the data, and the technology gets better because we expect it to get better. But what data are we talking about? This is an SRE conference, so it may not surprise you that I'm about to start talking about things that more specifically relate to SRE. So let's think about ice cream, because there is an ice cream stall outside, right? So imagine you run an ice cream gigafactory. You're really passionate about making ice cream. Let's look at this metric called product.icecream.count, which counts each ice cream product that we're making, and we're going to map the cardinality of this metric in three-dimensional space into a neat little cube. So you're an ice cream entrepreneur, so of course you make thousands of ice cream flavors, but for now let's only think about 3 of them: chocolate, strawberry, and vanilla. We also care about the size of the box when we're counting ice cream, so we get large, medium, and small boxes. And finally, we care about where the ice cream factory is located because it's easier to sell ice cream locally because people want ice cream residency. At this point, we have a cube. Each of the little cubes inside this big cube represents a single data point in the metric at a moment in time. Now let's apply this to a software system in the cloud. Our dimensions might become region, instance type, and role, and our overall metric is the count of apps that we have running at that time. Now let's talk about cardinality. So in this case, we call the cardinality of this metric the thing that we get by finding the product of the number of unique values within each dimension. Each of these 3 dimensions has 3 possible values, so we get 3 cubed or 27. Now this metric is going to be much more useful to us if we can see how it changes over time. So now we have a metric time series or time series. And in this example, this data is getting emitted by the system every 1 minute, which is also called the resolution of the metric time series. Another way to think about it is that with all the possible permutations in the dimensions of this metric, there are 27 possible different graphs of app count over time that you could draw. That's like approximately 27 there. When you're running an ice cream gigafactory with thousands of flavors and machines and millions of customers across the globe, you can imagine how those metrics might start to stack up. So they get sent to and managed in some sort of time series database. So we may end up with a bunch of high cardinality metrics in our monitoring system. Stepping back for a second, let's take a look at what we usually aim to achieve with monitoring. Firstly, we want to improve the system, otherwise make better ice cream. And secondly, we want to track service level agreements, or SLAs, so you know whether or not you're delivering the ice cream that you promised to your customers. So it's 10 a.m. on the factory floor. You look out at your army of sad factory workers who have been ruthlessly underpaying for the last year. Why aren't they working hard enough? Button presses are at an all-time low. They just aren't moving as fast as they used to. As you're thinking about what to do, one of the alarms in your control room goes off. Uh-oh, vanilla ice cream output has dropped below 80% of buyer demand. You run over to a screen to look at your monitoring, to search for the problem somewhere in your thousands of machines. And it's at this point that you realize that Sam from SRE has just pasted a piece of paper with a graph on it over the top of your monitoring setup. So nervously, you peel the graph away to reveal the dreaded words, cardinality too high, too many metric time series. The day has finally come. There's only one thing that you can do now. It's time to get your hands dirty. You venture out into the factory looking for the machines that make the vanilla ice cream. After about half an hour of intense searching, you finally get there, and it's a mess. Machines are broken, there's ice cream everywhere, and your workers are swimming laps in pools of it. But by this point, the children are crying, and you realize that you should have made your ice cream machines more reliable. The point being, one of the many benefits of having a system able to handle high cardinality is that you can more easily see where the problems are. We also care about monitoring because we want to track SLAs. So what about those crying children out the front? He does have two hands on the same arm. 100 of those children just so happen to have been in a payment plan for vanilla ice cream. And as per our service level agreement, they're entitled to compensation. So we're now in the difficult business of waiting for those children to leave negative reviews on Twitter before reaching out to financially compensate them. Ideally, they would just open support tickets. That basically means that we look like we have no idea what's going on, and if our monitoring system could flag those children affected by the outage earlier, then we could proactively reach out to them, which looks a lot better. So now we know what we want out of our monitoring, but why does that monitoring have to involve data that's high in cardinality? Here are some scenarios. Firstly, if we practice immutable infrastructure. This is the software equivalent of building an entirely new ice cream factory anytime we have a minor upgrade to any of our machines. To be fair, this is a lot easier in the cloud. Secondly, if we're doing blue-green, parallel, or phased deployments, or if we just want to monitor deployment IDs more generally, which is like refitting a duplicate ice cream factory and moving all of your workers to it because the other one is old and we don't like it anymore. Thirdly, for long-term capacity planning, like freezing 90% of your ice cream in deep storage because you never know when it could be useful. This results in the forbidden choc mold flavor. And lastly, if we're tracking SLAs at a per customer level, like calling each and every child to ask them about their ice cream experience. Let's put ice cream aside for a minute and look at Jira. So we run a multi-tenanted architecture for Jira at Atlassian. This visualization is a bit of a toy built by my team and myself in spare innovation time, which lets us see Jira in real-ish time, although I filled it with dummy data for today. It was built in A-Frame and 3JS, and it also works in virtual reality. This is Micros. It's an interface for AWS, and we use it as a platform tool for all of our internal services. Micros has a number of AWS regions that it operates in Asia Pacific, the US, and the EU. Each of these regions has a number of shards, which are groups of resources for tenants. Each of these shards has a stack, or at least one stack, which is a version of the code. And we swap between stacks in a blue-green deployment style to allow us to continuously deploy at least once a day. Each of these stacks has two groups of instances, EC2 instances for handling requests and normal operations, and SQS instances for long-running or asynchronous tasks. And if we look at all of those instances, the graph starts getting dramatically bigger. And if I were to try and map and animate all of the 2 million or something tenants or customers that we have using Jira, this graph would crash my laptop. And then consider the fact that each tenant has a number of individual users on it, which can be in the tens of thousands. So all of these things that I've just described are potential dimensions for metrics in Jira. Many of these metrics we collect only at the shard level, not the tenant level, because the cardinality required by per tenant metrics is just too high. The throughput of monitoring data at Atlassian has been a little bit like the Cambrian explosion, except instead of the proliferation of jellyfish, We have customers that keep signing up, internal services that just keep building up, and old, stale data that just sits around and doesn't do a lot. At Atlassian, this has led us to an unviable growth rate in time series data points, and we've had to take certain measures to dial it back a bit over the last few years, like downsampling and lowering metric resolution, for example. Let's take a look at the types of time series databases, or TSDBs, out there. So you've got SQL, and then you've got NoSQL or SQL-like databases. SQL time series databases are very friendly because everybody knows how SQL works, hopefully. They're convenient, familiar, queryable, and they integrate well with other systems. However, they're generally harder to optimize for scale, though it can be done. They're like a painting from the classical romantic period. Everyone sort of knows what's going on. Everyone's on board. It looks pretty. A good example of that is timescale DB. And then you've got NoSQL databases, which are in the vast majority. They typically outperform SQL-based databases, especially for time series operations, but the caveat is that they're largely unstandardized and sometimes miss functionality that you get in SQL, like joins, unions, having, etc. These can be hard to get used to because you have to learn a custom query language. It's more like a cubist painting. So you think, what's going on? But then when you look at it for a while, it starts to make sense, and you say, I could get used to this. So what are some popular time series databases, and what are some of the things that make them good? They can loosely fit into 3 categories: dependent, independent, and proprietary. Dependent time series databases depend on an existing DBMS for short and long-term storage. For example, Postgres or MySQL. You can think of OpenTSDB as a parent to many other TSDBs, being around for over a decade, and one of the first to offer a lot of features. TimescaleDB is a Postgres extension, which massively speeds up queries on time series data by partitioning it into chunks and then controlling chunk access through a central hypertable. Then you've got the independent TSDBs. They can use an external DBMS, but it's optional and usually for long-term storage only. Some interesting tidbits about these: with Prometheus, instead of using a push-based model where the system pushes metric data to it, it actually pulls metric data into it, which is supposed to help with debugging and retrieving data on demand. And you can also plug in Prometheus to use another non-default TSDB backend, like M3DB, which is becoming increasingly popular. InfluxDB developed a custom index that they creatively named the time series index, which uses a log-structured merge tree, or LSM tree, which is a common alternative to the standard B tree for time series data. It's also sharded, and it keeps hot data in memory and cold data on disk. Finally, you've got the category of proprietary systems that are closed source. These systems are pay to use if you can use them at all. A notable example is Splunk Infrastructure Monitoring, which was called SignalFx before it was acquired a couple of years ago. We use this at Atlassian for our monitoring and alerting. It's quite good at handling high-cardinality data. It uses one database optimized for bulk reads and writes for metric data, and the other one is optimized for search problems to store the metric metadata. I've also put Splunk, the logging tool, on here as well, because although it's great for logging, it can be used in some of the same ways as a monitoring and alerting tool as well. These next 3 you can't really buy. Facebook's paper on the internal TSDB Gorilla introduced game-changing compression back in 2015 with their delta of deltas encoding, which was exciting because it lets us reduce storage by 12 times compared to a typical workload, where memory is super expensive. 96% of all of the timestamps in this encoding are reduced to a single bit. And then you have Byte Series, which was developed a couple of years ago by ByteDance, which owns TikTok. They use a number of buffers to progressively compress data on entry. 80% of the size footprint of their ingestion is actually metadata, and they compress this by using a prefix tree to index tags. It improves on Gorilla's delta of deltas encoding by a factor of 2. Google's TSDB Monarch actually goes back to a relational model that looks very similar to SQL. It groups data by locality so that parts of queries can be pushed down and executed close to the source to boost the speed. And you've also got KDB, but we're running out of time, so I thought I should mention it because it uses a language called K and a query language called Q. Very cool. So why is high cardinality data dangerous? It's like a black hole. We can see that it's very scary and bad, but we feel ourselves getting pulled towards it. Firstly, you have an increase in query times. Our queries are iterating over more data. And for example, Prometheus can take 1.5 seconds to query over 100,000 time series, but 5 seconds for 200,000. It also increases storage requirements. Now you might say storage is cheap. We can just get a terabyte on S3 for $20 a month. But in order to optimize for read and write speeds, many TSDBs are in memory. So compared to traditional data stores on a hard disk or SSD, it becomes comparatively a lot more expensive to store data in memory. Luckily for us, the black hole of high cardinality is more like the black hole Gargantua from Interstellar, where once you go inside, instead of becoming human spaghetti, you just enter a sort of hyperdimensional tesseract prison that you can escape from if you do the right thing. So what is the right thing? Firstly, you can track the high cardinality metrics. If they're approaching high cardinality or are high cardinality, you can do something about them instead of waiting until they break. Secondly, only add dimensions to the data if they're useful and you need them in the immediate future. The vast majority of logs are never read, for example. Thirdly, periodically delete or downsample old data. Fourthly, collect data less often by defaulting to a lower collection resolution, and you can let users increase it if they need to. Fifthly, if you can't reach per customer visibility, then just settle for grouping your customers into shards and getting per shard visibility instead. And lastly, split up metrics. This last one deserves its own slide. If you've got metric A with 100 possible values for instance ID, 10 possible values for region, 10 for response code, and 10 for routes, then metric A has a total cardinality of 100,000. But what if none of our monitoring dashboards ever actually looked at instance ID and root at the same time? Then we don't need these two attributes to be in the same metric. In this case, we can employ poorly photoshopped knife Kirby to slice metric A into two separate metrics, metric B and metric C, which gives us a new total cardinality of 11,000, which is 9 times lower. And we're almost done, but before I go, I want to introduce an idea for further improving query times. It's a compression algorithm that I worked on a couple of years ago as part of my thesis. It's just a disclaimer, this is a proof of concept only. If this interests you, then please don't rely on my experiment results, as you will probably get different results. A decent analogy for this is that it's like the content-aware scale tool in Photoshop. When you use the content-aware scale tool to shrink or compress an image, the salient features in the image are preserved. For example, as the image here is scaled down, you can see that the person still has eyes, still has a mouth. It's important for us to understand that he's still a person. He is indeed a person. The algorithm is similar to some existing ones around roll-up or aggregating metrics on ingestion. You can think of it like downsampling, but instead of just being time-based, it's based on values and time. The best time for data to pass through this algorithm is before it enters the TSDB or between the write-ahead log and the database. But it can essentially act like middleware. On the left is a graph with dummy data of some percent CPU usage over an hour with 5-second source resolution. When the source data goes through the compression algorithm, we preserve the full resolution of the first X minutes of data, in this case 5 minutes, because if an alerting threshold is hit, we want to know immediately. And after that, all we're doing is recording data points that we think represent a statistically significant change over time. There's no point in recording full resolution horizontal lines in time series metrics. In this example, I set the algorithm to record data points where we see at least a 10% change from the previous data point. Using percentages like that allow us to change our resolution depending on the metric value. We could also just as easily tune the delta value to output higher resolution data if we're close to alerting thresholds, or tune it to care less about small values if we want. To give you an idea of benchmarks, we're just running out of time, this benchmark is a little bit sneaky because it's entirely defined by the input parameters that you choose. In this case, if I'd chosen to use an input resolution of 5 seconds, which I did, then it basically guarantees us a speed up. It also depends on the input data shape and the query that we're running. This query was a wildcard query to return all the time series for 4 different dimensions or tags in the database. Considering that, we see a 17 times speed up for query times and a 40x less storage reduction. And even when we change the original data resolution from 5 to 60 seconds, we still see a tripling speed up of the queries. And we also see faster write times and setup times for the database as well. That's just how the data was generated. You can check that out later, and how it was implemented and tested. Some caveats: we basically lose the ability to compress our timestamps because our timing now becomes irregular, and it's less effective for data that changes a lot. It's highly variable. To wrap things up, sorry if you haven't watched Interstellar for the spoilers, and I'm even more sorry if you've ever worked in or adjacent to ice cream industry, because some of that presentation was bordering on slander at an industrial scale. In case you're wondering, some of the images you saw were generated by DALL-E on openai.com. Thank you, USENIX, for having me and hosting this, and I'm happy to answer some questions now and on Slack afterwards. And thank you for coming to my talk.